Are you interested in what inverse kinematics is? Do you want to know how it works? Do you want to implement your own inverse kinematic simulation? Well, this is the perfect place to learn all of that. As you can see on screen, I have a bunch of end result simulations that you'll be able to make after learning inverse kinematics and how to implement them. We see segments that resemble an arm, one that resembles a string, another that looks like a sort of wave. Finally, the last one could be any of these but attached to some point. If you want to learn how to create these or more and how they work, then keep watching. So what is inverse kinematics? Inverse kinematics is the process of getting the angles of joints as they move towards some point. You can imagine we have some points here representing joints and lines connecting them. They want to move towards some point represented by this purple dot. We'll rotate the line and make the end of the line the new point that we want to go to and repeat that entire process. Let's see it again. So we'll rotate the line, we'll make the end of the line the new point we want to go to, and then repeat the process for all the other lines. And let's see it one more time. Okay, great. Using that technique, we're going to implement this using C++ and raylib. There's also a GitHub link that has all the code in the description. Let's start with all of the files we'll need. We'll need a Makefile, a main file, a RealVector segment and SegCollection class, along with their header files. So we're going to start by making our Makefile. The Makefile is used so we can easily compile our program. So first we have our executable name, which we're going to call example. We're going to have our compiler, our libraries, and our sources that are required, our target and prerequisites, our target being the executable name and our prerequisites being our sources. Finally, the script, where we compile our sources with the output being the executable name using the libraries. Next, we're going to start on our main file. The main file is where we have our main game loop playing and where everything is rendered. So we're first going to initialize our window with a screen width and screen height and a title, Inverse Kinematics. Next, we're going to create our game loop, which while our window should stay open, will continually draw a white background. And finally, if someone closes the window, we'll call a function that finishes up all processes. That is the start of our main function. Now let's see what we have so far. So if we run make, we can compile our program into an executable called example. If we run example, we see that it shows up with a blank canvas. That's what we have so far. We'll come back to the main function to add more functionality later. So next we're going to want to create our RealVector header file. The header file contains everything that we'll need to implement in our actual class file. So here we have our x and y variables representing our position, our RealVector constructors, and 4 functions, which are vector addition, vector subtraction, getting the magnitude of the current vector, and getting the angle of the current vector. That's it for our RealVector header file. Now we're going to want to write our RealVector class. So this is going to contain everything that we need to implement from our header file. Starting off, we have our constructor. So this just sets our respective variables to what they need to be. This next one is our vector addition function. The one after that is our vector subtraction function. Then we have a function that gets the magnitude of our current vector. And then finally we have a function that gets the angle of our current vector. Now we could use this in all the other classes that we'll need it in. Now that we've implemented our RealVector class, we can use it to help write our segment class. First, we're going to need to write our segment header file, so let's start with that. We're going to need our variables, so a vector A and B, the length, angle, and thickness of the current segment. We need our segment constructors to set those variables, and then we're going to need 4 functions after that that we're going to use for our segment. And that's all we need for a segment header file. Okay, now we could finally write our segment class. This is probably the most important class as it has most of the inverse kinematics logic. We could start with our constructor, which has all our initializations, starting with our A vector, which is the start of our segment, then our length, angle, and thickness of the segment, and then we call the update function, which initializes our b vector, the end of our segment. Now, the update function is just a wrapper for the calculate b function, and then the calculate b function, as in the name, calculates our b vector using the information it has. Next is probably the most important function, our follow function. So this function moves our segment to a particular point using the algorithm I described at the beginning, where we alter the angle of the segment and then move it. So this first chunk of code here in the segment, in the follow function, finds the angle that we need. We do this by creating a vector t, which is the point we want to go to, and then subtracting the vector t by the vector a. Here's a little representation of that. So we have a vector a, vector t, and then t minus a is a vector that goes directly from a to t, and that angle in the bottom left of that vector is the angle we were looking for. Now we set that angle to the angle of the segment, and then this part of code moves the segment using that angle that we found, and returns it. Now I'm omitting a little bit of information here as to why we're not updating the value of b, and why it's even a separate function, but just know that it's relevant for when we want to add functionality to lock the segment in place. Next we have our show function, which is just gonna draw our segment for us. That's it for the segment class. Okay, now let's see what we have so far. First I want to change the screen width and screen height because I thought it was a little bit too small for the demo. Then let's include our segment header file so we can use our segment class. Then let's actually make our segment class. We'll call it seg, and we'll give it a position 0, 0, length of 200, angle of 0, and thickness of 5. Then we can go ahead and make it follow our mouse. Oh, yeah, all right. Let's follow our mouse's X and Y position. Then we can update the b vector using the function that we had, and then we could show our segment. Okay, awesome, that's it. Now we could compile our program and then run it. And here's our segment, all of that code for this segment. Okay, we're almost done, just a little bit more after this. Okay, we're almost there and almost done. We just have 2 more things left. This one is the SegCollection header file. This one's pretty simple. We have a vector of segments, not the vector we made, but the one from the standard library. And then we have our constructor and 4 functions. That's it for our header file. Now we could finally make our SegCollection class. This is the last one we have to write, so that's great. We can start exactly with the goToPosition function. This function will move our segment collection to a certain position. First line here just checks if we have segments. This next chunk of code does the same algorithm that I described at the beginning, where we move a segment to a certain point and make the start of the segment the new point we want to move to, but for all the segments. And then this last chunk of code right here, it will update all the b vectors for every segment. You may be wondering why not just do that in one loop, why we need another one. That's because if we want to lock the segment into place, then we'll need a structure like this. If you see those commented lines, they're important for that. So we have the normal algorithm where we will move the segment, make the end of the segment the new point we want to move to, and do that for every segment. But then we move everything back to the point we want to lock it into place in too. And that's what those comments are for. If we change the start point before we update, it'll end up moving everything back. Then we have a ShowCollection function. This shows all the segments. We have our change start point function. It will change the start point of a segment. And then finally, last but not least, we have our add segment function, which will push our segments into a vector. Now that's it for our SegCollection class. That's everything. Okay, now we can demo everything. So let's get rid of what we have here right now. These are unnecessary. And let's include our segment collection class. Then let's initialize a SegCollection. Let's make the examples from the beginning. So first we'll start with something that's sort of an arm. So we add those segments here. Position doesn't matter. The length would be, let's say, 25 times I plus 1. Angle doesn't matter, and thickness of 5 for all the angles. Then we could say segments that go to position, get mouse X, get mouse Y. We could make and then run it. So here is our sort of arm. Now let's make the second example. So something like a string, right? So we could have, let's say, 500 segments, and each one can be 1 with a thickness of 5. So length of 1, thickness of 5. If we make, we could see we have a really fluid segment collection here. Alright. Now for the next one, it was like a giant wave. We do that by, we could keep this the same, and then we could just make the thickness I plus 1. So for each segment, it's going to get 1 unit thicker. We could run it, and we have something like this. Pretty mesmerizing, crazy. Now for the last one, we had it attached to some point. So how we did that is, if we go to a segment collection, we have these commented lines. If we just uncomment them, it will lock this every segment collection to the position 100, 100. So 100 units on the x-axis, 100 units on the y-axis. It's going to lock it there, but if you change these numbers, it'll lock it in a different position. And now if we make and run it, we could see that it's locked to this position right here, and it can't move beyond that distance. Looks kind of weird, but yeah, that's it for everything. Now you can make any sort of inverse kinematic simulation. Everything's working. It's great. And finally, I wanted to say thank you so much for watching. This was more of a project for me. You have no idea how long it took to get all this done, way longer than it should have. But I hope you learned something, and yeah.